Okay, hello everyone. Good morning. Thanks for coming to this symposium and inviting me. Well, an organizer invited myself. It's nice to see you all. And I will talk about properties of algorithmic information distance, which is based on conditional Kolmogorov complexity, which had great success in the past. And I will show you some of these success stories. And in particular, this distance is a metric, and I will study the metric properties. There can be additional properties like Euclidean or bounded or whatever. And interestingly, there has been not much theoretical study of this distance, of this very curious and powerful distance in the past. So I'll do that now. And one way to study properties of a metric is via isometric embeddings. So isometric embeddings are distance-preserving maps between two spaces, and they can reveal, then if you know something about this space, they can reveal the properties of this other space. Okay, and in particular, Euclidean spaces are particularly interesting. I mean, they're important, and also if a distance is Euclidean, or some people don't call infinite dimensional Euclidean spaces Euclidean, they call it Hilbertian or embeddable into a Hilbert space, but I just use Euclidean. That's easier to pronounce. And so if a metric is Euclidean, then you can do all these kernel methods and so on. So it's a quite useful property to have. So this algorithmic information distance is based on the shortest program, which transforms a string X to a string Y and vice versa. So captures all algorithmic regularity. And I mean, this is just a survey. I will come to define all these things later. Okay. And as I mentioned already, it has seen a great success in phylogeny reconstruction, usually in its normalized form. And we know Kolmogorov complex is not computable, so we have to approximate it somehow, and you can do that via standard compressors. Okay, so the main goal is to initiate a deep theoretical study of the unnormalized distance decay. And the reason for the unnormalized one, I mean, it's a little bit more, it looks easier and tractable, and it was already difficult enough to get to the results I wanted to have. I have the feeling that the normalized one, probably most of these results go through. It's just a matter of, work or doing it. But, sometimes there are surprises. But there were enough difficulties, and there are enough open problems, and we'll come to them in the end already with the unnormalized one. Okay. And then, what are the fundamental properties, beyond being a simple metric? So, and what does isometric embeddings give us? So we can, try to embed. So B star is the space of all finite strings, and dk is this Kolmogorov distance, which I will define in a second, which is, for now, is the conditional Kolmogorov complex of x given y and y given x and the max of both. Okay. And so assume we can embed that into some other space where we know some properties. For instance, it's Euclidean. Then this positive property will inherit to the, I will call this space now Kolmogorov space or B star k, just, otherwise it's a mouthful. So if we can embed the Kolmogorov space into some Euclidean space, then we automatically know that it inherits the Euclidean property because it's a subset of it, and something is Euclidean, and a subset is, of course, also Euclidean. So that's a way of proving positive properties. If we do the embedding in the other direction, so we scale embed some known space with some negative property, for instance, say not Euclidean, into Kolmogorov space, well, then it will inherit sort of, again, in this direction, the negative property, because now we found a subspace of Kolmogorov space, which is not Euclidean, therefore the whole space cannot be Euclidean. But on the other hand, if we have some positive property, again, Euclidean, take convexity or geodesicity or something, and we embed it, then we cannot say that this whole space has this property, but we know that there's a subspace which has this property. And we will see, for instance, that Kolmogorov space is quite generous allowing embedding all kinds of spaces, so which is quite useful. So if you limit yourself to this subspace, then you inherit a lot of good properties, including the Euclidean property, actually. Okay. Okay, so that's all what I've just said here. how to study this metric properties. And before I do so, I will give a very brief introduction to Kolmogorov complexity, because I assume everyone knows this. And then the algorithmic information distance, also very briefly, and the normalized version, and the applications it had, and then we'll come to the new stuff. Okay, so Kolmogorov complexity is defined, or the conditional Kolmogorov complexity of x given y is defined as the shortest program which takes y as an extra input or oracle, or you glue it to the program and outputs x. Okay, so that's the shortest program which transforms y into x. Okay, and if you have any, so that's for strings, and if you have any object which is not a string, then you just encode it as a string. If you have an image, naturally all objects are now files on a computer. Files are your byte string or bit strings, and you just, take this natural encoding. There are many possible encodings, right? The JPEG and whatever, right? So, but you take some natural encoding, take the bit string, and so if I talk about the Kolmogorov complexity of an object, then it just means the Kolmogorov complexity of a natural encoding. And if codings are computably transformably into each other, then it also doesn't make any difference for the Kolmogorov complexity, apart from additive constants, which are always floating around anyway. Okay, so you don't have to worry about which natural encoding you use. In particular, probably the only thing, I'm counting up strings and natural numbers at a few points. So the Kolmogorov complexity of natural number is, you encode it in binary somehow, and then you ask for the shortest program after you encoded it in binary. Okay, so if you have simple strings, like the string of all zeros, then of course there's a very small Kolmogorov complexity, because, well, you write a very short program, print zero loop, n times, and then the program has size, well, you have to specify the n size log n, okay? On the other hand, if you have a random string, or you take a picture from nature where there's a lot of noise cannot be compressed, then it will have high Kolmogorov complexity. Okay, and so the definition is nearly independent of the choice of universal Turing machine. So this gives it this universal nature, and it satisfies most properties of an information measure. The Shannon information measure, or any sort of information measure, should satisfy. One can probably even most replace by all, but you have to be a little bit careful. So it inherits virtually all linear relations from Shannon entropy. And a big downside is that it's not computable, okay? And we have to approximate it in practice. And don't worry too much about the additive constants. These days data sizes are huge, so these additive constants usually don't matter. But the incomputability is a problem. You have to approximate it, and every approximation has some limitations. Okay? So in summary, K is an excellent universal complexity measure. And well, I'm not talking this lecture about Occam's razor, but just to emphasize this, there's no science without Occam's razor, as we have heard in other talk by Leuenberger and others. So it's also a suitable way of quantifying in a universal and general way Occam's razor, which is, for instance, needed for AGI and ASI, because there we ask about, machine learning algorithms which work in general and not some specific ones. Okay. What properties does Kolmogorov complexity have? So first, of course, I can encode every string by just print string in quotation marks, but I'm talking about the prefix complexity, which does not know where the program ends. It is sort of self-delimiting program. So it needs to find its end. In order to do so, we have to also encode the length of the string, which we can do in 2 log L of x bits. So that's the reason why you get this upper bounds. This is not too interesting for this talk, because most of the new results are only within a logarithmic slack anyway. Many of the traditional results also. Don't worry about this log. It's nice sort of to get order 1 in constants, maybe as a sort of intellectual sort of challenge, and various Kolmogorov complexity results are with order 1, but many are not. So, and yeah, at the beginning I was ambitious, but then I had to give it up. Okay, Kraft inequality, extremely important, which essentially tells you that most strings are incompressible. So a string is incompressible if the Kolmogorov complexity is larger than its length. It cannot be much larger, as we have seen by just a naive encoding. And that the Kraft inequality shows you that. So if you have any prefix-free code and you look at the lengths, then they always satisfy this Kraft inequality. And Kolmogorov complexity is the length of a prefix-free code, therefore it satisfies this Kraft inequality. Okay. So this lower bound here holds for most x. Okay, that's duplicate here. So that means also that the Kolmogorov complexity of n, here's n is an integer, goes to infinity when n tends to infinity, because there cannot be infinitely many natural numbers or strings with a bounded complexity that would violate the Kraft inequality. Okay. I'm listing these properties just, it's good to know. And second, because that's the ones which I will exploit in the results. Extra information, can never make the code shorter, and extra information you can never harm in making your code longer. That's pretty obvious and trivial to prove. And then you have the symmetry of information, or what Gabriel Leuenberger called it, a chain rule, which is actually a better name, right? Which is also in Shannon entropy, it's called chain rule. So maybe I should rename this. I think Leon Vitani called it symmetry of information, because you get the symmetry kx is equal to kxy is equal to kyx, but that is the trivial part. The highly and the lower bound is also greater or equal is also quite simple, because if I have a code of y and then I take this y and then I code x with the help of y, of course I have a code of x and y, and k of xy is the shortest code, therefore I have greater or equal here. The smaller or equal, that is really a deep result in algorithmic information theory, and very particular to the non-resource bounded Kolmogorov complexity. As soon as you add resource bounds, this doesn't hold anymore, which is a big pity. Okay. Information non-increase. So if I transform my data in any computable way, I cannot create new information. So the Kolmogorov complex of f of x is smaller than k of x, plus maybe some information I've snuck into via this function f. MDL bound, a very important bound. This says, so if I have some string x, and I have a probability distribution p, and I want to encode this, I can use Shannon-Fano coding or Huffman coding or arithmetic coding, and encode that in minus log p of x bits. Well, if I know p, so I need to also encode p. So together, I have a code now of x, and we know Kolmogorov complex is shortest code, therefore I get this inequality. Again, relative to Shannon-Fano coding, are very easy to prove inequality. But so this is the basis of the minimal description length or minimal message length principle. So what you do there is, in all of modern machine learning, what you do is you model your data by maximum likelihood, which is minimizing minus log p of x over a class p. But then you can overfit, and to avoid overfitting, you regularize. And the regularization is done in all kinds of ways in practice, and in theory, you should regularize by the Kolmogorov complexity of your model, which is done here. And then you minimize the right-hand side, which approaches in the limit of a sufficiently rich model class and an algorithm, which of course can find this. It's amazing how well stochastic gradient descent works in practice. And then by other arguments, you can argue the closer you get to Kolmogorov complexity, the better your model will predict, and that's a famous Solomonov bound. Okay. Okay, again here, as mentioned, a big downside is it's only semi-computable, not finitely computable, but it's upper semi-computable. So just, there is an algorithm which approximates Kolmogorov complexity from above, and after finite time, you get the correct value of Kolmogorov complexity, but the algorithm doesn't hold, and you never know whether you're already there. Okay. So it's, it could be worse. So I always say, up to delta 2 in the arithmetic hierarchy, that's sort of in the realm of realism. And beyond delta 2 is just fantasy. And that lives even in upper means sigma 1. Okay. Or pi 1. Okay, so you cannot compute it. But luckily, I have a halting oracle from a long time ago lying around, and I used this to compute Kolmogorov complexity. And here's the graph. Okay, so have a look, because it will vanish as soon as somebody detects my lie. Okay, so what we have here, I've shown you the upper bound. So x is here now a natural number, and the natural number I can code in log n bits plus the length, which gives you the log n. So that is definitely a rigorous upper bound. We also know that for most strings, the length is at least log x because of Kraft inequality. So you have this lower bound, and log x plus log x, and this is very tight, right? It's very close for most string, right? We have a very good understanding, but that's just the random strings, right? Which maybe not the most interesting ones. But then, you can have very large numbers, say 2 to the 2 to the 100. It's a very large number, but has a very short description. So you will get these dips. But if 2 to the 2 to the 100 has an easy description, then also 2 to the 2 to the 100 plus or minus 1 or plus or minus 2 have an easy description. So we have a sort of very weak form of continuity that if I have an easy to describe number, then in the neighborhood, these numbers are also easy to describe. So we have this, if a dip is deep, sort of, then it's also wide, right? So that's the reason, why this plot looks like this. Okay, so quick slide on the relation to Shannon entropy. So Shannon entropy is defined over random variables or probability measures. So in discrete case, you just take p log p summed over all x and minus, that gives you the entropy, and similarly with the conditional entropy. And if you look at the properties of Shannon entropy, they look exactly the same as in Kolmogorov complexity. And indeed, what you can do is, if you have any inequality which is true in Kolmogorov complexity, you just take the expectation with respect to this probability distribution. It holds for all x, so it also holds with, in expectation with some p. And that gives you then approximately the corresponding bound in Shannon entropy, which is not so nice, right? It's just approximate, and here it's exact. But you can make the strings arbitrarily long and then divide, so you can recover the Shannon inequalities exactly from the approximate Kolmogorov complexity inequalities, which is quite neat. Yeah. The other way around is also possible, but that is highly non-trivial. There's a paper in 2000 by Romanchenko or something like this, and Alexander Shen and others. It's also in their book. They have a book on algorithmic randomness and whatever the title exactly is, in 2017, I think. So it's a very neat proof, but quite non-trivial. And I adapted their proof for my for some of my results. Because this duality between Kolmogorov complexity and entropy is really useful. Sometimes it's easier to think about finite strings, and sometimes it's easier to think about just entropy. So a disadvantage of Shannon entropy that it only holds sort of in expectation. And so also as a side remark, in classical statistics, even in Bayesian statistics, you can never talk about, is this string random? This question is sort of illegal. Yeah? It doesn't make sense, right? Also, it's so natural, right? You see a randomly looking string, and then you see all zeros, and you ask which string looks more random. Sorry, you can't ask this question. And with Kolmogorov complexity, you can do that. Okay, so now I come to the distance, which forms then the core part of the new talk. So when is a string or an object similar to another object, and there's a universal solution? This is just take this conditional Kolmogorov complexity, which is very natural. So if there's any algorithmic similarity, then the program will exploit it, and it can be a little bit shorter. If not, then if y doesn't help, you will get a large number. So it's a very natural distance measure. For instance, x is very similar to itself naturally. Just copy input to output, has length order 1. If you process some information x, the Kolmogorov complexity will also be 0. We are already seeing, some problem here. So if I take x and delete it, right, x is not very similar to the empty string. So that is no good. It's not symmetric, so we have to do something about it. And in a second, and a random string, is a very complex. I mean, according to sort of, standard information theory, and any conditioning doesn't help unless it peaks into this randomness. So you just get the length of this random string plus the log terms. Okay, so 3 problems. It's not symmetric, it's not normalized, and it's not computable. Okay, so we solve these problems now. Symmetrization is easy. We just take kx given y and ky given x. And now it's symmetric. So why the max? It's not super critical. You can also take plus, right? And possibly, you know, other choices. And the argument here was that they originally started with, we want a program which can transform x into y and also y into x, so the same program. And you could think, okay, you have a program x to y and y to x, you know, these are two programs with two lengths. So the sum of the lengths definitely allows me to transform in both directions. So maybe I should use the sum here. But there's an interesting theorem which they proved is if you have a program of length 1,000 converting x to y and a program of length 100 converting y to x, then there is a program just of the longer length thing 1,000 who does the conversion in both directions. You somehow can exploit in one direction to the other. I mean, you somehow invert this function, but you know, there's tricks to it to make it work. Okay, that's the symmetrization. And then if you have very long strings and they differ by 20 bits, you say, okay, you know, two images and you change a couple of pixels, right? They are of course similar, right? But if I give you the 100 digits of pi and the 100 digits of e, you know, they're totally different. So you want to normalize that by the length maybe, and the correct thing to do is by the Kolmogorov complexity. Then it's nicely bounded by 1. And yes, and what you can show is that this is actually a metric, which is quite neat. So metric, that means additionally, I mean, symmetric, non-negative, satisfies the triangle inequality. You have to be a little bit careful, but I will come back to that later. Okay, so final thing is we have to approximate that, and we can just use some standard data compressors. Think about a self-extracting RKF, and if you run this is a program which reproduces your string X, right? So this is definitely an upper bound. So we just take some standard compressors like gzip or bzip, and that's what I indicate with T. So that the T is a decompressor now. In the experiments, the group chose gzip or bzip, so some standard compressor, so no domain-specific knowledge integrated. There's also some theory, although LampleZip is not really a good compressor. I always recommend, if you want a theoretically neat compressor, which has great practical properties, I suggest the CTW, the context-free weighting. It's a Bayesian mixture over double exponentially many variable order Markov trees, which you can compute in linear time, so extremely efficient. And it's exact Bayesian. It's very beautiful, works very well. And we have also some experiments, and Tim talked about this, how language models can be trained of using that. So CTW is worth to check out if you like Bayes. Okay, so that's fine. So now we can take two strings or objects and compute the distance, and we get a number between 0 and 1, 0.3, say. I mean, what do we do with this number? It's just a number, okay. So we take a bunch of objects now and compute the pairwise distance. Then we have a huge distance matrix, and we can stare at it, which is sort of not so much fun. But we can try to approximate this matrix now by a, say, minimal spanning tree, which then gives us, some structural information about how the distances between these objects is. It's not exact, right? But, it gives you the gist. And, it's better rather than taking a minimal spanning tree. So if you have, say, 3 points, minimal spanning tree would be then, 1 point in the middle and so on, some L shape or something. It would be better to have a point in the middle and then some star shape or so, assuming these points are approximately the same distance. And this is called a Steiner tree. And you can also compute this. It's an empirically problem, but the approximation algorithms. And then you can apply it to various domains. And one domain, which this group, Rudy Cilibrasi and Paul Vitani applied it to, is mammals. And they took the mitochondrial DNA. DNA is over the base pairs A, C, G, T. It's base 4. I mean, you can just take 2 bits, then you have a binary string. And then you take, I don't know, a monkey and a human, and you concatenate. Oh, what I forgot to, an important trick here is, it's a little bit annoying to sort of do a conditional compression, right? Usually you compress a string. So, but now we use this deep theorem that k of x given y is about k of xy minus k of y. And then I have rewritten this in this form. So we only need to compress strings concatenate strings and then compress jointly and, do the difference minimum and maximum and so on, and you're done. By the way, whether there's a comma or not doesn't make any difference within logarithmic accuracy, okay? Okay, so you do that, and if you do that with 24 mammals, and then so you compute the distance matrix and then the tree, and what you get is this diagram here, and this perfectly reconstructs the phylogenetic tree of these mammals, which is pretty amazing because GCIP or BC2, and I can't remember which they used, definitely has no biological knowledge built in. Okay, I mean, it's correct according to the biologists. And under the carp is not a mammal, and you see sort of they threw a carp in, and you see it's completely separate here. I mean, you can also look at the numbers of the matrix that I have it in the paper, and to confirm this. This gives you the qualitative picture, and then the numbers give you sort of the quantitative version. And so this was at the time in 2005 that went through the press worldwide. People were very excited about it. They applied it to all kinds of other domains. I just present one more. They took the Declaration of Human Rights, which has been written in all languages. I mean, they needed the text written in all languages. I mean, nowadays you just use Google Translate or some language model, and compress the language separately, compress it jointly, and if you join it and the language is similar, then you can compress it better. Blah blah blah. Compute the distance matrix, the Steiner tree, and what you get is a nearly perfect reconstruction of the evolution of this mostly European language, I think. There is some problem with the alphabet. I think Greek is wrong, if I remember correctly. So, but I mean, it is also very impressive, I think. I mean, now these days you throw everything in the language model and it also gives you an answer. But I mean, it has all the knowledge from the internet, so that's not fair. Okay, so here's a list of other things they applied it to, including the classification of SARS viruses during COVID, and so on. Okay, so this concludes my background slides, the old part, and now I come to now there's two more slides which are sort of not really new. Okay, so let's start with some theory. So I defined this complexity metric, which I also call algorithmic information distance or algorithmic information matrix. So it's all the same. Via this symmetrization via max. I will not normalize now because it was enough work to go through the normalized version. And what I also do is, but that's not really absolutely important, but it's very convenient. I add a small constant CU, that's a universal constant. If x and y are different, and if x is equal x, I mean, it's of order 1, I set it to 0. Okay, this constant is order 1, and this one was naturally order 1, so I change the natural definition by just a slack of order 1, and we have these slacks anyway, so it's sort of a fair modification. And if I do this modification, then you can show it's a proper metric without any slack, which is really nice, right? So you have, d of x is 0, exactly no slack. I mean, it was already always larger than 0. Obviously, Kolmogorov complex is always larger than 0. And now the triangle inequality is actually satisfied. And, the reason is now we have, we have added CU twice on the right-hand side and only once on the left-hand side. And if CU is sufficiently large, this order 1 slack goes away. Yes. Okay. Okay, so now we have a real proper metric, which is nice. Here's one example I want to mention because, I mean, the goal here is a bit different to the goal before. The goal before was, find a metric which exploits all similarities. I mean, that is sort of probably still the goal when you apply it. But here the goal of this work is to find out what properties this metric has. And for this, I need an embedding, which is not just, an upper bound, but sort of exact. I mean, within logarithmic terms. Okay. So here, for instance, if I have the string 0, 0, 0 and 1, 1, 1, I mean, the Kolmogorov distance would be close to 0, right? Because, I mean, it's trivial to flip all these bits, right? I mean, in this case, the strings are also trivial. So what I would have to do is, say, take an image, a real-world image, which has high complexity, And then I just say negate the color. So like, good old, film thing, negative or so. So the transformation is trivial. So the Kolmogorov distance would be just, order 1. While the Hamming distance or any, Euclidean distance or whatever would be very, very large. Yeah. And so this is what I don't want. I want now to embed, if I have two objects which have a certain distance in my original space, I want them to have the same distance in Kolmogorov space. Otherwise, I don't learn anything. Okay. Okay. So one property has been proven about this algorithmic information distance by Bennett and others in 98 already. That was, I think, also the paper which defined the normalized information distance, first one. And so let us call a distance admissible if I take a ball. I mean, balls are very important, right? If you metric space, you take a point, you pick a ball with finite radius, and then you ask about the properties. And in discrete spaces, you can ask about how many points are in this ball. And we don't want too many points in this ball. So let's call a distance admissible if there are only finitely many points in any ball of finite radius, which is very natural. If you take any finite dimensional space, you take a grid in d dimensions, you make a ball, right? You compute the discrete volume, it's all finite. I come to the continuous case later, right? Because there you always have infinitely many points. But okay, so let's call this distance admissible. And so I will so phi, I will come, the details all come later. So phi is now a mapping from some metric space to another metric space, in this case, Kolmogorov space, strings. And what you can show is you take any metric space, so V is the space, dV is the metric, and then V are the elements, and V prime, you look at the distance, and you map them into Kolmogorov space. Then the Kolmogorov distance will be bounded by this distance as long as it's an admissible distance. So any distance which is admissible, reasonable, or whatever, right, is larger or equal than Kolmogorov distance, which is a formal way of saying every structure which is in your domain can be extracted and makes the distance smaller. Okay. Yes. So the distance has been called universal in this sense. I mean, I just call it now minorization universal because it's not universal in the sort of isometric. It's not isometric universal. Yes? Sorry, what? So that's the space where the points live in. So, R to the n or Z to the n or whatever. Yeah, sorry, that comes later. And the converse, if dk minorizes some distance, then d must be admissible. It cannot have infinitely many neighbors. Okay. Okay, so now I come to isometric embeddings, if there are no further questions so far. Okay. Okay, so here's the definition. So I have two. So V is a set, R to the n or so, and in this set you have a distance, and I only consider metrics. And you have two of these metric spaces, and you call a mapping from one space to the other. It doesn't need to be onto. It can be. I mean, in this case, obviously, it needs to be an injection, but it doesn't need to be a surjection. So you have this mapping, and you call it an isometric embedding if, well, you have a distance here in the V space, you transform the V's into the W's, and then in the W space if the distance is the same. Okay. And it needs to be injection because if you take two different points and map it to the same point, by the definition of a metric, then the left-hand side would be 0 and the right-hand side would be non-zero. So you can't have that. Okay. So that's the definition in general of an isometric embedding. And then the specific one if W is the Kolmogorov space. But we will see this is not really suitable because, I mean, Kolmogorov complex is always an integer and, metric spaces are not integers. So we have to somehow deal with this. Okay. So there's a very nice result, and it's actually quite easy to prove. And I also have this in the paper. I mean, I put the proof in because it's so nice and easy. Every separable metric space can be isometrically embedded in L infinity. Okay, so L infinity is just R to the infinity, so infinite dimensional vector space with the infinity norm, the subnorm. Okay, and what does separable mean? If you don't want to know, then just think about a countable space of countable size. Separable means that the space has a countable dense subset, and from a practical point of view, all spaces with matter for anybody except mathematicians are separable, right? In physics or anywhere, because if there's no countable dense subset, you can never ever approximate it. So separable space is all you need in life, except you're a mathematician. Okay, so every separable metric space can be embedded L infinity. Wow, this is really great, right? So L infinity is all you need. The problem, there are multiple problems with this. I mean, usually you have extra structure which gets lost. And also L infinity is itself not a separable space. And I just told you separable space is all you need. But I mean, it's an interesting, very, very old result. Okay, so that means, of course, also as a corollary, that Kolmogorov space embeds into L infinity, which is sort of nice, right? You have this very obscure distance and you think maybe, this doesn't fit, to any other space. It's not compatible or so. But no, there's a subspace of L infinity where Kolmogorov this space lives happily in. Okay, and this is constructive. Modulo that Kolmogorov complexity is not computable. This mapping is constructive and quite easy. So you can come up very easily with this long vector. Essentially, it's the vector of all distances of x to some reference point. Okay, that's the embedding. Okay, so that was this direction from Kolmogorov space to normal spaces, but mostly I will deal with the other direction. Okay, in the other direction, we have to do a little bit more with our definitions because first, all algorithmic information theory has this additive slack, which is a problem. And second, Kolmogorov complex is an integer, so we cannot embed a metric which is 1/2. So this is too strong of a condition. But what we can do is we can just easily scale it. So assume we have a metric here. So there's a metric space and there's some points here. And maybe these points are 1, 2, 3, have distance 1. The distance between 1 and 2 is say 1. If you multiply a metric by a large number, S, through the whole talk, it's still a metric, right? And usually all the properties are also preserved, right? So we just multiply it with a large number and ask then, can it be embedded approximately in Kolmogorov space? And well, there's a teaser with this regular triangle. So what I can do is I just map each of these corners to a random string. And okay, I should have put up the definition here. So what I mean is k random and k independent strings. So in statistics, you know what random is and what independence means. And there's an analog notion in Kolmogorov complexity. A k random string is just a string which is incompressible. Kolmogorov complexity is maximal. And k independent means that if you compress it jointly or separately, you don't gain anything. So it's a very natural analog of either the conditional independence in probabilities or the analog of in Shannon entropy that the entropy of x comma y is equal to entropy of x plus y if the random variables are independent. Okay. So I will usually, when I talk here, drop the k. So I just say independent and random. Okay. So if these are 3 independent random strings of length s, and I ask what is the conditional complexity of this string given this string? Well, this string doesn't help at all to compress this string, and this string is incompressible. Therefore, the length will be s. Okay, so all these conditional complexities are s. So I get a regular triangle back, apart from the log s slack, which for s to infinity doesn't matter. Okay, so that's the way, and that's why I call it scale embedding. So here is the formal definitions. So now I have this map phi indexed with this s with a scale from my metric space to the space of strings. And we call it a scale embedding, or should we call it scale isometric embedding? And then, string scale isometric embedding. I think it's a little bit long. So I just call it a scale embedding. The same as before, you map these to strings here, but you're happy if it's equal to s times the original metric, and then this little s on top means that the difference is bounded by log s. So this is within logarithmic accuracy. because this scales linear with S, the log slack is then really small. Yes?
Because kept mentioning that Kolmogorov complexity is an integer number. That's
Yes.
like a problem.
Yeah.
But isn't this d sub k metric that you're using a rational number? Not that this changes much, but
no, it's also I don't normalize. That's the unnormalized one. Yeah. Yeah, that's a good point. Yeah. Yeah, for the normalized one, I don't need the scaling probably anymore, because I mean the scaling in the numerator and denominator. Okay, that's a nice thing about the normalized one. I mean the scaling, it doesn't harm, but it's yeah. Okay. So here, so you may be, okay, that is lame, right? Now I have this approximate embedding, and I lose, my exact properties and so on. But well, that's not the case. So if you have this approximate embedding for every S and you divide by S and take the limit S to infinity, because the ratio is now the error term is log S divided by S, it converges actually very rapidly to your true distance. So you can exactly recover your true metric as before. It's the same trick as I mentioned before, how you go from approximate Kolmogorov inequality to exact Shannon inequalities. Okay, so yeah, I mentioned this. Okay, so we have a collection here now of embeddings, and there's a stronger notion. This collection, I wasn't so happy with it, but I mean, if you think about Kolmogorov complexity results, it's always, for sufficiently large string, this holds, and you have sort of this sequence of strings. It's all in Kolmogorov land, we are used to it. But there's a nicer way of doing it. So let's do an embedding into infinite sequences. So when I say string, it's always finite. When I say sequence, it's infinite. Okay. I embed it into infinite sequences, and then I look at the finite initial part of length S or proportional to S, and ask, do I get a scale embedding for all S? So formally here, I take V of phi of V, and then I cut it at f of s comma v, which is usually just often independent of v and just proportional to s, maybe 5 times s or something. Think about just s, okay? And I cut it and ask it to be s times dv, okay, for all s. And that is sort of neat, right? You have an infinite sequence and you want the initial part to nicely embed. So that's a stronger notion, because of course can recover. So if I have a sequence embedding, then I also get a string embedding. The reason is still to deal with the string embeddings. Some results are a bit harder, or quite a bit harder to get with the sequence embeddings. But I think I have all results now transferred over to sequence embeddings, if I remember correctly. Okay, so let's start with an example. Embed the Hamming space. So that's the hypercube of dimension m with the Hamming distance. Okay, and so the nice positive result is, yes, that scale embeds into a Kolmogorov land, and I will build up. I will come to more general theorems later, but it's a important building block. Okay. So we take the strings of length 4, but you really have to think about a string of length, so, okay, these are now also strings, so don't be confused. So these are the strings. So B to the M is my metric space, which I care about. And, in this case, they're also strings, but it's a different string space, okay? And you have to think about here longer strings. No, actually, you don't. Okay. So what do? I get some k independent k random strings. So if the string has length 4, then I need 8. Okay. And I map then, if it's a 1, I map it to at position 2, I map it to W2. And if it's a 0 at some position, I map it to V1. Okay, as this diagram here. Okay. And then I combine this. And I get this. So these are now strings each of length S. So I have a strings of length 4S. Okay. And it's very easy to see now that the conditional Kolmogorov complexity is S times the Hamming distance. Because let's take two strings, string U and a string V is used up, U prime, and just change a little bit, one bit here, okay? So then these two strings are the same. So the embedding is the same except for V1, right? V1 is replaced by W1, okay? If I look at the conditional Kolmogorov complexity, well, I mean, to encode these ones is very easy. I copy it from the input to the output, and the only thing that remains is to encode the W because that's different, independent from V, and encoding the W1 because it's random takes S bits. So I get S for flipping 1 bit. Yeah, 1 scale gives S, and flipping, multiple bits gives you then a multiple of this. Okay, so that's very easy to see. Now, many, especially graph metrics, embed into the Hamming cube. So if I take, any graph, I can say the distance between two nodes is the length of the shortest path. Okay, so that's called the path metric over graph, or I just call it graph metric. Okay, and so if I have this little tree here, so this star here with 3 arms, this star will come back later and play an important role. So I can embed that easily into the Hamming cube. So the middle here I embed into 0, 0, 0. And the 3 legs here I embed into 0, 1, 0, 0, 0, 1, or 1, 0, 0. Obviously, the Hamming distance here between these is 1, and the Hamming distance between the outer ones is 2, which exactly is the same as in this graph, right? So the node in the middle has distance 1 to the arms, and the arms themselves have distance 2. That means I can also embed this star graph into Kolmogorov space. Okay, and indeed, you can embed all trees very easily into the Hamming cube, and I come back later. Many graphs, but not all graphs can be embedded into the Hamming cube. If I could embed all graphs, then I could, also embed all graphs into Kolmogorov space, but it turns out this is not the case. Okay, yes?
Like the trees, does this embedding somehow resemble like mango trees or
Maple trees?
like Robert, like the hash trees, you know what I'm talking about? For versioning.
No, I'm not. No, but it's very easy. What you do is you prove this by induction. You assume you have a tree of n nodes, which you can embed in a cube of dimension m minus 1. Then you create an extra dimension, go to m, right, and place the new node in the extra dimension. This new node, because it's a tree, is only connected to one node, and so you place it on top of where the other nodes are, and that's it. Yeah. Yep.
Question: when you say that not all graphs can be embedded into Kolmogorov space, you mean just not by this trick, or is there also?
At the moment, I mean, well, in the end, I will show you that it's not possible anyway. But for a long time, I tried this trick, and this, because not everything can be embedded here, sort of, I needed other routes. Yeah. Both is true. Any other questions? Okay, good. So now, this is a discrete space, and I could embed no more discrete spaces. So for instance, if you have, maybe I'll mention a little bit. So if you just have a line, okay, a line is a tree embeds. Okay, we're done. If you have a grid, right, you can also, the tensor product between two graphs which also embeds by just taking the tensor product of two of this Hamming cube. So you can have any finite grid already embedded in Hamming space. You can get quite far. Okay, but now what is this continuous spaces? I mean, continuous space, of course, don't embed, right? Because Kolmogorov complexity is discrete. Wrong. Okay, because the embedding does only need to be approximate. I can just discretize. So let's take the interval from A to B, or just think 0 to 1 with the absolute distance. If it were discretized, right, to some epsilon grid, it would just be, a graph, a line, and a line, I could roll it in bed, apart from the scaling, and we can always fix the scaling. So we would be done. And that would be one way. Essentially, it is just, rather than discretizing, having the line, and then embedding it somewhere in the hypercube, I show you the more direct path, which is instructive. So I need 2 random strings here of length s, okay, two strings. Sorry, this is the proof for if A is 0 and B is 1, and then you scale and get the general proof, okay? So what I do now here is, so the trick is a little bit similar. Where's T R? So we want to embed the real number R, which lives in the interval 0, 1. Okay. What I do is I multiply R with S, the scaling. Well, it's still not an integer, so then in upper bound or lower bound doesn't matter. I get one T. Okay, that's an integer now. And then I take the first T minus 1 bits from the random string Y, and then I take the remaining bits from this string Z. Okay. And if I do that, and again, I don't show that because it's pretty obvious. I take the conditional complexity of one R given R prime. They only differ in the middle part, right? Because the tail is the same and the spinning part. And where they differ is between T and T prime, which is just S times R minus R prime. And these bits I have to encode. And because everything is random, I just encode them then in S times R minus R prime bits, or the absolute bar if it's in the reverse. And I have my scaling embedding. Okay. So that is nice. So I can now come with that also continuous structures. You know, at the beginning I thought, okay, you know, we have this limitation, but that's actually not a limitation. And, you know, you still think, you know, okay, what is going on here? Well, I mean, we do that for every S. So that means every 2 points, which are separate in the original space, will be eventually separated if the S is sufficiently large. Yeah, because I showed you, you can go exactly back. So you really don't lose anything by this discretization. Okay, so back to graphs. So far it was success. And so let's ask, can we embed all metrics with 5 points into Kolmogorov space? And the reason I'm asking for 5 points, because for 4 points I was able to show in a originally laborious way. There's no absorbed. And you know, if we can embed 5 points, then we can also embed 4 points. And the reason why I'm not talking about 6 points, because 6 points come later. And then 7, and then 8, and I talk forever, okay? Okay, here I'm talking about all matrix spaces, not just graph matrix, okay? But let's first look at the graphs. So all 5-node graphs, they need to be connected, otherwise the distance would be infinity, and that's not allowed. So all connected 5-node graphs are there. And it's a nice exercise to try to embed all of these into the Hamming cube. And then you try to, and then this embeds into Kolmogorov space. And you know, it's the 3, 3, 3 easy. Okay, that's something, this is easy, you know, this is just, you know, you see the Hamming cube, and this is just in the 3rd dimension poking out. Okay, what is with this here, pentagon? Doesn't work, right? Hamming cube is a bipartite graph. No problem, we just put extra nodes here in between, then it's not a pentagon, then it's a decadon, right, with 10. And then we can embed it in the Hamming cube. You just, if you cube, you go this, and then you go on the other side back, and you have embedded. It's just a factor of 2 bigger, but you know, we don't care about the scale. Also done. Okay, nice. And you do it with all this, and it always works nicely. It's not very hard. And then you get to this graph here. And you try, and you try, and you try, and somehow it doesn't work. Okay. So finally, I have a much more, and you can prove that it doesn't work, okay, into the Hamming cube. Okay, so then I thought, okay, maybe it also doesn't embed into the Kolmogorov space, right? You know, and then you try to disprove things, and you know, try and try and try. Okay, so that was the history, and now, so what is the real proof here? Because I mean, I care about beyond, you know, graphs. Okay, so the space of all normalized 5-point matrix forms are convex. People typically talk about polyhedral cones, but I mean, it's easier, I think, mentally. Everyone knows what a convex polytope is. So what you do is you just say, you know, the largest distance or the sum of all distances normalized by 1. And then, you know, then everything is finite. And then we get a convex polytope, because if you have 2 metrics and I take an average of 2 metrics, it's not a metric. Nice. Okay. So this forms a convex polytope. With 5 points, I have 10 distances. Where's the polytope, right? So I take all the distances, so there are 10 different distances. So it's a vector in 10-dimensional space. And then some vectors are metrics and some are not, right? And this forms the convex body, and it's easy to see that it's a polytope. Okay. So if this convex polytope, and we know for a polytope, any point in the polytope can be represented as a convex combination of the corners. Okay. So if I can show the corners in bed, I'm done. So I need to find the corners of this polytope. And there are a lot of corners. Yeah, they are double exponentially. So if you have n points, you're double I think it's double exponentially many. But there's lots of symmetry, and I only did the one which are non-isomorphic. And for 5, there are only 3 essentially different corners, which is nice. And 2 corners are trivial, corresponding to these kinds of graphs. And then we have 1 corner which is left, which is, well, exactly, I mean, it doesn't look like it, but it's exactly this graph here, okay, which doesn't embed. Okay, so that's a proof that I can embed any metric, which is a linear combination of all these corners if they don't involve this graph, okay? Well, so I worked quite a long time, and, after a long time, I found a, now in hindsight, relatively easy construction with some XORing. So before, what I always did was independent random variables, and I combined them somewhere, I took some here or there, and that didn't work. Okay, so what I have to do here is I had take some random variables and XOR of these random variables, and then the construction works. You can find it in the paper. So I was able to embed this graph. And then I got really excited. Wow, even this graph embeds, maybe, all graphs embeds, even larger ones. Yeah, we will see. Okay, so all 5-point matrix spaces embed in Kolmogorov space. Well, so in order to, okay, next chapter. Any questions here? Yep.
You talked about positive properties that you wanted to.
Yes, yeah.
These spaces, specific properties, I'm happy to find as subsets of the space.
So here I talked about, okay, the only special property about these matrix spaces here are that they're finite. Later we'll talk about primarily one norm spaces, a little bit infinity norm spaces, and Euclidean spaces. That's the essential properties which are only considered. Yeah. There are other properties. You can ask whether a metric is geodesic. For instance, a geodesic means that for any points you find points in between, such that the distance from A to B plus distance from B to C is the same as A to C, so that's a straight line. And a Kolmogorov space actually satisfies this, which is nice, so it's geodesic. And there are lots of other properties you could study, but I haven't touched most of them. Other questions, comments? No, okay. Yeah. Yeah.
So the other thing about this metric, you were again mentioning that it's the issue with it is that it's nature.
Yeah.
Have you considered using the negative log solve?
Yeah, good idea. No, I haven't tried. And I mean, you also have the additive constants floating around. So it's an integer, but the additive constant also kill you there. So it's not real help. I was thinking about it and discarded immediately. Maybe there is something you can exploit extra, but I don't see it. Okay, so these results were sort of rather elementary. And in order to get, more advanced results, we did some more advanced tools, which were not available, so I had to develop them, okay, which I will do now. And that's random scale embeddings. It's connecting to probabilities and random variables and so on. Okay, so first, very important old result is that if you sample some string X, it doesn't need to be string, but I only care about strings. Is that true? No, they're from other spaces. No, okay. So doesn't matter. So you have any random variable, string valued or whatever, and you sample it from P, then we know that with high probability, we can encode it in minus log p of x bit. I mean, there's a theorem that, you know, the expected code length is like this, but the variation is very small. So with high probability, it can be encoded in this many bits. And we know that this is the optimal code. We also know that Kolmogorov complexity is the optimal code. Therefore, they must be equal. Okay. It's related to this MDL bound and randomness deficiency and optimal coding. Okay. And that's what I exploit. The same then is true for the conditional Kolmogorov complexity. So if I can find random variables so that minus log p of x given y symmetrized satisfies my properties, you know, then, you know, I can also have the embedding into Kolmogorov space via de-randomization. So this holds with high probability. Therefore, there exists strings. Sorry, obviously it must be a string here. Well, I can encode it, yeah. Okay. So then with very high probability, if that holds with high probability, and only probably 1/2 or anything non-zero is sufficient, then it means there exists a string such that it's satisfied, and then I just pick this string and I'm back. Okay. So yeah, so that's the strategy which I just mentioned. I construct a random embedding and then I de-randomize. Okay. What can I do with this? Well, I can go further. I can prove now that any bounded subset of R to the M with a one norm scale embeds into Kolmogorov space. So now we're getting sort of real, I mean, double sense, right? Okay, bounded subset, I mean, is essentially, you know, in a hypercube, and then I scale the hypercube, so it's essentially 0, 1 to the m. I've proven already 0, 1. So what's the path? Well, I take the 0, 1 embedding, randomize it, then I use a product space embedding theorem, which I will not present, but I will explain briefly, and then I de-randomize and I'm done. And okay, first, I now also have a randomization theorem, which was quite tricky to get by, but it's too weak to actually to be useful. But it's very easy to take this construction for the interval and make it directly random, right? Just replace the Kolmogorov randomness by random variables and it works. So I have a deep theorem that any Kolmogorov embedding can be randomized, but that is too weak for this purpose, okay? But anyway, I can do it. And the product space embedding works very simple. So I should have put it on the slide. So because the one norm, right, is just the sum of two absolute values, it factorizes, right? You embed the x coordinate and you embed the y coordinate and you sum it up. Okay, in the original space, the summing gives the one norm. In the Kolmogorov space, you just need to be careful that these embeddings of the x coordinate and the y coordinates are independent statistically. So you use independent random variables and you're done. Okay. So that's, you know, it felt natural, right? You know, Kolmogorov space has this additive property if it is random. L1 is additive. So yeah, and it worked out nicely. Okay, let's see what comes next. Okay, so that is the positive result so far. I get more positive results, but now let's look at some negative results. Any more questions? I think we're good in time. Okay. So remember Kraft inequality, which tells you that the neighborhood size is bounded. So if I take a, let's call Kolmogorov space, I take some string x, I take some radius r, and I ask how many points are in this ball of radius r. They are less than 2 to the r. Kraft gives you less or equal, but I mean, it's easy to see that it's strictly less, but it doesn't really matter. It's 2 to the r. Okay, so here, so if you have distance 1, you just have 1 point. If you have distance 2, you have 2 extra points. Distance 3, you have 4 extra points, and so on. Okay, so that gives you a bound. If you now look on the other hand at some infinite dimensional spaces, you know, LP is interesting, the infinite hypercube is interesting, the infinite Hamming cube is interesting, but you know, take a very small space, take just all one hot vectors, but infinitely long. So it's all zeros, and at one place is a 1. So it's I zeros, then a 1, and then infinitely many zeros. Just take this one. And the distance between any two vectors is just 2, right? It doesn't really matter. You know, any P norm, right? This is just, sorry, yeah, whatever, right? I mean, the Hamming distance, the one norm is obvious, and the other ones, because they live on the axis, right? It's just two, right? And now I put a ball, an epsilon ball, around each corner. I can even take a big ball of size 1, right? So, oh no, sorry, I don't have to talk about balls here. That comes next. So I take this ball of radius 2, and I look at neighbors. I take a ball of radius 3, and I look at neighbors which have radius less than this or less or equal. Well, I find infinitely many, right? So take this sequence 0, 0, 0, 0, take a ball around it. In this case, I need just 1.1 or so distance, and I have infinitely many points which live in the neighborhood. Okay. So therefore, I cannot embed this space into Kolmogorov space because it violates this admissibility Kolmogorov craft inequality. And well, B infinity, the hypercube, is just a superset of this, and you know the Hamming cube and the hypercube is a superset, and the LP space is a superset. So they all don't embed. So roughly speaking, infinite dimensional spaces don't embed. Okay. Yep.
I see it. I was thinking, well, since you scale,
Yeah.
maybe the balls are allowed to have more points, and so
Yeah, the theorem is not that trivial. You have to take into account, but it doesn't scale in the right way. You're right. Yeah, it's a oversimplification. Okay. Yeah, I just told you the reasoning. Sloppy reasoning. Okay, so but now let's look at continuous spaces. I said if the neighborhood is infinite, you can't embed. That was also sloppy. I mean, the 0, 1, right? I take a small ball, it has infinite neighbors. It does embed, right? So the real negative theorem is a little bit more subtle. So what you have to do is, so we take this space here and look at epsilon balls and ask, can we embed, how many epsilon balls can we embed? If the answer is it is more than 2 to the some scale factor SR here, then you have a negative result. And if it's bounded by 2 to the S times R, here you see the scaling. Yeah, if it's super exponential, so if it's just 2 to the SR, any S, you know, it will be fine. But if super exponential doesn't work anymore, okay? Yes, so that's the negative result for continuous spaces. And you see the 0, 1, right? You can fit only finitely many epsilon balls in the interval or in a finite dimensional cube. But in infinite dimensional cube, you can fit in more. Okay, that was one negative result. Let's come to another negative result, you know, for finite spaces. I mentioned already the path distance of graphs. And now we looked at the graph K32, which embeds. Okay, then I try K33. Okay, it also embeds. Nice. Then I tried K34. I couldn't embed it anymore, but that doesn't mean that it's not possible, right? I was just not able to. And then after a long search, I finally looked at K33 with one edge removed. Okay, which is actually the graph which I showed you originally, but you know, the order of things which I tried, you know, was not the order I'm presenting here, right? Okay, so that's this nasty graph. Sorry, that's no, that's not the nasty graph. That's the nasty graph with one edge added. So no, it was not obvious from the K23 how to go to the K33 without E. Okay, so I'm not that stupid. So okay, you remove one edge, and I spent a lot of time, and then, you know, I got desperate and I ran out of time, and I just, you know, I realized I can solve it brute force. I mean, it was not guaranteed that I can get a negative result, but there was a chance. So I ran 32,000 linear programs with 64 variables and 432 constraints, and the computer said no. Okay. That's a rigorous proof. I also added an epsilon slack if you don't trust numerics, although the solvers are pretty good at doing it themselves, and the slack is huge, right? So even with large slack, it's not possible. So it's really a proof, okay? So where do the 64 come from? I will not talk about the details. So there's 6 nodes, and each node is sort of there or not there, sort of in a certain sense. It's 2 to the 6. This gives you the 64 nodes. And then for the distance with the sum, so k of x given y plus k of y given x, I only have to solve one system, which is nice. But with the max, it's not a linear program anymore. But what I then did is I just, okay, if the max is equal to something, either the left-hand side is equal or the right-hand side is equal. So that gives me, well, because I have 15 distances, that gives me 2 to the power of 15 possibilities, which side is sort of equal and which side is smaller. And then just have 2 to the 15 linear programming problems, which I can run through. And the computer was quick like this. Even, laptop with single core. It's amazing how good these linear solvers are. There are packages which can then extract the offending inequalities and can effectively give you a sort of a natural proof. The natural proof may still not be short, but I expect it fits then on a page or something like this. You deal with all these inequalities. Sometimes they are so short, that they're insightful. I always found it in classical information theory. Okay, we have this inequalities, apply this inequalities, or if this mutual information is 0 and this is 0, then this is 0, and so on. I always found them very uninstructive, and I now know why there is no systematic way of dealing with this, because there's a nice recent paper from 2020 which proves that this is a formally undecidable problem in general, which is insane. Yeah. And here I was lucky because there are so-called Shannon inequalities, which you all know, which you find in textbooks. And I just checked whether the Shannon inequalities are violated, and some are violated, and then I go to Kolmogorov space. But there are infinitely many more of these inequalities, and there is no systematic way of enumerating. You can systematically enumerate, you can have a semi-decision procedure, but not a decision procedure, and there's still active research to find this. So you don't get a polytope anymore. So if you have a polytope, but with infinitely many faces, it's rounded in this space. So it is quite interesting, this area. Okay, so unfortunately, the big dream of embedding all metrics is shattered here. So there's a 6-point metric which doesn't embed in Kolmogorov space. Okay, finally to Euclidean properties, which Boumediene is so eager. Okay, what I call Euclidean is often called embeddable into Hilbert space, but that's too long. And embeddable into Hilbert space means there is a mapping from X to a Hilbert space, such that and you can map any Hilbert space with inner product to L2. So you can always use the 2 norm in L2. And if the L2 norm of these feature maps equals the original space, then it's embeddable to Hilbert space, which some people call Euclidean, because if it's finite dimensional, then it is Euclidean, and if it's just infinite dimensional Euclidean. Okay. And a very important tool, which I will not talk about much, or not at all, is how can you, if you want to embed, you find embedding, you're done, which can be hard, but it's possible. But how can you prove that such an embedding does not exist? There's a very useful tool, which is called conditional negative definite criterion. So you take a finite subset of points, then you have a distance matrix, and you ask, is this matrix not positive definite, but negative definite with some extra sort of condition? And it's embeddable in Hilbert space if and only if this criterion is satisfied, which is really neat. So you reduce it to a finite dimensional problem. Any finite dimensional subset you take, if it's always satisfied for all the subsets, you're done, and you can embed all the points, which is quite remarkable. Okay, so it's a very useful tool. So here are some natural Euclidean metric properties. So if you can embed something in Euclidean space, then you can embed, of course, every finite subset. And I just told you how to prove the reverse. So that's, you may not sort of initially believe this, but it could be true, and it is true. Okay, that's why we call it natural. So every separable Euclidean Euclidean space, yes. ISO embeds into L2. That means all infinite dimensional Hilbert spaces are equivalent, right? That's another theorem. And, you know, it's, you know, you have this distance matrix and you diagonalize, and it's also natural. If you have two Euclidean spaces, then I can take the product and take square root d square plus d square, and then it's also Euclidean, right? I mean, it's just like this Euclidean norm squared. I mean, you look at this, I mean, obvious. And okay, this is for Boumediene here, this note, and it's not a deep theorem, but a warning. So for any metric space, not Euclidean, I can always add a constant and make it Euclidean, or raise it to a sufficiently small power and make it Euclidean. But what I'm doing here is, you have this metric, you add a huge constant, what you create is a regular simplex. And the regular simplex, of course, embeds. But you lose all structure, right? It's a discrete metric, right? So yes, you can do it, yeah, but you totally ruined your original metric. So if you want to do it, this constant is better to be small. Otherwise, it makes no sense. And with the power, it's also very easy. If you take a metric to some small power, all the properties are satisfied, and the triangle inequality is also easily shown if the power is smaller than 1. It's also just a one-liner. So these are natural. And now I come to some weird stuff. Okay, so wake up. Even so, you start with the Euclidean metric, you take it to a small power, it's still a metric, fine, easy. But it stays Euclidean. So if I take the Euclidean distance in 3D, you know, and take the square of it, it's still Euclidean. And it is totally absurd, right? What happens here, I mean, you cannot embed it, you know, in 3 dimensions anymore. You need infinite dimensions, but it always works. It's pretty amazing. Yeah. And also, every Euclidean space embeds into L1. So you can always take your Euclidean space and points, you know, embed it somehow in another R to the infinity, and take the one norm, and you have a perfect isometry. It's also wild. But here, the last one, I take the one norm and take the square root. It's Euclidean. Okay. Yeah, I mean, I just have to tell you that it's true, and you can dig through these proofs. It's very old results. I mean, this one is a deep old result, and that is sort of a simple corollary in a certain sense. Okay, so I will exploit this now to get some more good results. Okay, so, well, first some negative result. Okay, dk, unfortunately, is not Euclidean, which was a big disappointment. I mean, it was to be expected. But the proof, you know, you have to do a little bit. And here is back our little fellow, the star graph. And I want to show you the proof here, because that is, you know, neat. Okay, first we saw we can embed the star graph into the Hamming cube. Okay. I also showed you how to embed the Hamming cube into the Kolmogorov space. Also neat. Okay. So now let's try to embed this into Euclidean space. But here you see a different difficulty. So the distance between these 2 points here, the legs, is 2, and here's 1 and 1. And we know in Euclidean space, they must lie on a perfect line. But then it's also true for these legs here. So you have 3 points which lie on a perfect line, and you have another point which lies on a perfect line. Therefore, it must be either on the other side and have distance 3, or it must be this line has distance 0. It can't have distance 2. You're done. So this does not embed. Okay. So now let's assume we could embed Kolmogorov space into L2. Well, then I could go this route here and embed my little star into L2, which I just showed is impossible. Therefore, you can't embed the Kolmogorov complexity into L2. So that was easy. The harder part is the other direction. You can show that locally it's Euclidean. So you can take any finite set of points in an Euclidean space and map them somehow to strings into Kolmogorov space, look at the distance, and then respect the distance. Okay, which is without, you know, adding large constants. Important. Which is nice. And okay, I should call it another negative result. And can I give you an intuition? I thought I have the proof here. Let's see what comes next. Okay, another negative result is, so I cannot embed decay into Euclidean space. But then I thought, okay, we know if I take alpha to a sufficiently small power, I can embed any finite space. And that is sort of cheating, not interesting. But the Kolmogorov space is infinite. So if I could find a small power and it still works, then that would be a non-trivial and potentially useful result. Okay. So I looked at small powers, and for a while, square root I couldn't rule out, and then I was able to rule the square root out, and now I'm down to 2.92. So maybe it still embeds if the power is 2.29. I highly doubt it, but I can't prove it. Okay. I need some more fancy graphs and show some negative embedding results, or using this conditional negativity, some results. And I mean, it's probably a matter of work just to do it. Okay, so this is just a visualization of the results. So here, you have R to the M with Euclidean distance and some points. And here, so it's not possible to embed the whole Kolmogorov space into Euclidean space, and also not the whole Euclidean space, into Kolmogorov space. But if you just take finitely many subpoints, then you can, from this direction, you can always embed, and from this direction, there exists such sets that you can embed. Okay. Yeah, this is just, just think about a two-dimensional, sheet of paper. I mean, this is just explaining the picture. Okay. Okay. Yeah, here is the proof that decay does not into Euclidean space when P is equal to, but you can strengthen this proof. It also doesn't embed into one norm space or any P norm space. Okay. And this is the proof here. So what you do here is, so the embedding that is not embedding, that is not Euclidean, that is somewhat easier to prove. So look at this diagram now. So we have decay, and we have seen, I mean, I've claimed that you can embed this bipartite graph K23 into decay, so that works. But I've also shown that decay 3 without an edge, and this is sufficiently related. You can also show that DK3 is not Euclidean. Okay, so this embedding doesn't work. And you can also show that you cannot embed it into L1. But that's what I mentioned sort of in the very early when I had all these graphs. So this also doesn't work. While this really weird theorem, you can embed all L2 into L1. But let's come back to that later. So what we have here is if we could embed decay into L2, then I could embed the K23 curves into here and into here, which is a contradiction because it's not possible. So this proves decay is not Euclidean. Yeah, okay. And via this very deep, weird, old result, I can also do in this direction here, right? If I could embed decay into LP space, here, this is a result from LP, you can go to L1, and then I could embed this K32 to here, to here, to here, and I have a contradiction. Okay. So that is the most sort of powerful negative result I have. So you cannot embed it into any P norm space. If P is between 1 and 2, I don't know what happens if P is larger than 3. I would guess it's also negative. Okay, that's it. I'm good in time, so I have some time even for the summary slides. So that is the properties, the positive and negative properties. So first, I mean, it's really nice that decay is a proper metric. And it can embed rich variety of discrete and continuous spaces, like bounded subsets of Euclidean space, of the one norm space, and discrete spaces like the Hamming cube, and therefore finite grids and so on. It's fundamentally not Euclidean, but it's locally Euclidean in the sense that I can embed any number of finite points. And yeah, but sorry, I can embed any finite Euclidean metric, but I cannot embed any finite metric because this 6-point graph showed that it's not possible. Okay, so what maybe let me come first to the negative results and then to the relaxing thing. Okay, so here are some open questions. There are many more in the paper. So you can ask, is decay universal in some more restricted sense, right? You know, like, I mean, we know, yeah, okay, I'll leave it like that. What I have not studied now is endomorphisms, automorphisms from Kolmogorov space into itself. You would think, okay, I mean, it's sort of trivial, right? I just take strings and pipe them through some computable function and so on. But the way I define the scaling bettings, you have to scale it up. So it's less obvious than it sounds, okay? I mean, you could say, I mean, why care about scaling bettings, but if the goal is to get scaling bettings, then this question becomes non-trivial, okay? Another question is, so I showed you finite grids embed, does maybe the whole set of M embed, okay, or R to the M then later, okay? And, maybe, not all graphs embed, we know that, but maybe graphs with special properties which are important, maybe all bipartite graphs embed. I mean, I was able to show up to K33, so maybe the higher ones also embed, okay? I have results already now that, that you can achieve the embedding of unbounded spaces if you relax the conditions of our scaling embedding a bit or a lot. So let's recall this definition. So we said dk must be close to dv in the sense that the slack is only logarithmic. And additionally, the constants c and b do not depend on v, so it's uniform. There's a good reason for uniformity, because if you allow non-uniformity, then what you're effectively doing for every fixed s, you have embedded only a couple of these strings with reasonable accuracy, and the other one is, just garbage. Yes, you can increase s, and then more and more gets into it, but this sounds like a uniform embedding, and then you should just do nested embedding. That's sort of probably equivalent, and that's the reason why I didn't go this path. The log was motivated, first, I can do it, and second, from Kolmogorov complexity. 1 second. And so, but if you relax the uniformity assumption, and you go from log s to just little o of s, or square of s or whatever, then, you can embed also unbounded spaces. Yes, there was a question, comment?
I think you kind of answered it. I was wondering, is this like maybe a typo? The S is missing inside the absolute value.
Yes, there's an S missing. Yes, yeah, thanks. Yes, I have some more. I saw there's a paper out there, and I have some more results and ideas. If somebody with a good theoretical background is excited about this and wants to sort of take that to the next level, happy to share what I have so far. Yeah, that's it. And but that are some of the references. That's my new book. It's freely available online if you want it quickly or easily or conveniently. This is the paper. Where's the paper? Here, that's the paper on arXiv. And yeah, Bennett was the initial paper for the normalized information distance, and the other papers, Okay, thank you very much for attention.